Great. Uh-oh. Perfect. Okay. Hi, everyone. This week, we're very happy to have Chen to tell us about axions and cosmology. Now, whenever you're ready.
Thank you.
Yeah, everything good?
All right. Okay, great. Thank you. So yeah, today I'd like to share with you some of my work that I did with my colleagues in Israel. So to look at the ultralight dark matter and try to constrain it using the galaxy kinematics. But before that, I'm really impressed by the university. I even checked the review. Look, it has 5-star review, and it has good review as well. Not just by our colleagues, but by the general public. So yeah, sorry, that's the only joke I prepared. Yeah. I mean, the Euro story that says that the Americans tend to start with a joke, and then people from Asia tend to start with apology. So sorry, that's the only one, so I've done both. We all know that the axions, they were originally motivated by the strong CP problem as an elegant solution. But beyond the QCD axions, they also show up in many UV theories, in some string theories, for example. And interestingly, they provide a very intriguing dark matter candidate, mostly because of the misalignment production mechanism and many variations of the misalignment mechanism. So these are some of the reasons why axions and axion-like particles could be interesting. And phenomenologically, we know that the mass of the axion could vary across a large range. And depending on its mass, the phenomenology can be quite different. For example, when it's around 10 to negative 20 EV or below that, their very existence can imprint on the galaxy rotation curves. And when the mass is slightly heavier, the photon to axion, I mean, if they couple the photons, the photon to axion en route conversion could bias the cosmic distance measurement. And that's related to some of my previous work that I did to use the cosmic distance measurement to constrain the axion photon coupling. And at even higher mass, they could, in principle, form the self-gravitating bosons and condensate structures, the so-called boson stars. And the merger of a pair of boson stars can emit gravitational wave, which turn out to contain interesting information about their potential. And at even higher mass in the radial range, recently we showed that the axion decay, actually the stimulated decay of axions, can give us interesting signals at the radio telescope at places like SKA. Okay, so today I'll mostly just focus on the very light end to show you that how we could look for axions, the very existence of axions using the galaxy rotation curves. But that's roughly the context.
So sorry, you say you are going to concentrate in the 10 to minus 20 electron volt.
That's right. Around that mass range. Okay.
You don't care if
we can
it
chat
is-
about the other mass range.
It's like fuzzy dark matter in that case, or
I mean, this is that's where I'm going to is related to the fuzzy dark matter. I'll start with the usual fuzzy dark matter. And then if I have time, I'll try. I mean, I'm for particles, so I care about the actual model realization. So I'll try to show you a few twists, a few variations, and how, for example, the PQ scale can change the bounds, and how the self-interaction coordinate, for example, can be rather.
sorry, I didn't mean to interrupt.
Yeah, no worries. Yeah, please do ask questions if you have any. Yes, already.
Yeah, is that like matter if it's a CPO and CPE that you consider your previous props?
So I should say here, at this scale, the CP property is mostly not important right now. So that's why I'm saying, like, let's just look at the quadratic potential and look at how gravitationally they will imprint on the rotation curve. But yeah, if you think about the photon couplings or the axion EB coupling, that could be relevant. Okay. Good.
Super radiant bounds, what's the cutoff?
And the super radius?
Yeah, I thought 10⁻20 was already cut off. No?
Okay, so for the super radius, if I remember correctly, there's a small band over here. That bounds the self-interaction from below. That's roughly saying that if you have large enough self-interaction, the super radius will not happen, and the bound will be suppressed. And that's from the supermassive black hole, roughly at this. And there's another one around 10⁻11-ish. That's from the stellar black hole. So there are two bands that bounds the self-interaction from below. Okay.
So your self-interaction is always assumed to be strong enough that you're evading the bands.
So for this mass range, in a large mass range, the super radius is not constraining.
It's not a constraint.
Yeah.
For super light.
I mean, super radius is only valid for a small range.
You need the mass to be roughly the size of the black hole.
Exactly.
And so if you go to even lighter masses, then that also turns off super radiance.
Oh, I hadn't appreciated that. That's weird.
Yeah, the source of the confusion is the way that is always plotted.
Yeah.
That is a misleading. That enhances the radius.
So you would need enormous black holes if
In
you-
order to cover that lighter.
Right, of size galaxies.
That's right.
Right, that's right. So I'll put this into the context of the size of the wavelengths, just in case.
Right.
Okay. So if we start with the vanilla, the quadratic potential, and this is the equation of motion for the axion of the homogeneous background. And that is the reason I'm showing this is that it's important for the production, right? Because in the beginning, when the Hubble friction, this term shows up as a friction, is large, much bigger than the mass. The field value is frozen, so that in the physical volume, the field value doesn't change, and in the co-moving volume, it increases, and this is the origin of the misalignment mechanism. And once the Hubble drops low enough, since if we want to look at the structure formation, we should look at those k-modes, those fluctuations that are non-relativistic. So here I'm taking the non-relativistic expansion, and this is the equation of motion that governs the if you look at the right-hand side, the psi here is the Newtonian potential that is sourced by everything, including if it clumps here itself, so it should have itself, and any other components that has a density fluctuation. So I mean, this is the so-called the Schrödinger-Poisson equation, and the punchline here is that if you look at the simulations at large enough scale, meaning that the fluctuation is small enough, then this kinetic energy or so-called quantum pressure is not important. So they simply fall into the gravitational well, and they start to clump. And at large enough structure, the ultralight dark matter reproduces most of the structures of the cold dark matter. But then the question is that can we distinguish these two scenarios, and how do we look for ultralight dark matter and to distinguish it from the usual cold dark matter? And the trick here is to compare the scales between these two. And because we know that gravity has this tendency to put things into a confined region, a small region. But from the uncertainty principle, we also know that once it's put into a small enough region, it will have a large kinetic energy, so large that it counterbalances the gravitational potential, the gravity contraction. So therefore, there is a critical scale where these two terms balance each other. So that is the usual Jeans scale that we derive. And below this scale, the pressure wins so that the structure formation is suppressed. And that is the usual bound on ultralight dark matter we know that comes from the structure formation with observables such as lambda alpha and subhalo mass function, etc. That shows that below a certain mass range, the ultralight dark matter of this type of potential can only be less than roughly 20%.
I just want to make sure in your previous slide.
Okay.
What's the delta rho? And the rho, what's the derivation?
Okay, good. So right here, I'm writing delta phi. What I mean is the fluctuation of phi. So this way of writing it only holds when it's a perturbation. So later I'll show you that in the nonlinear regime, this actually takes up the whole field value. And delta rho is just the density fluctuation other than ultralight dark matter. Suppose it's a subcomponent of less than 100%. Then this delta rho should contain the metric, that source is the metric fluctuation by anything else.
So in the gravitational potential side,
Okay.
side terms, do you have a do you only care about the perturbation, or you also have some background piece should include there?
So this depends on whether my scalar takes up 100% dark matter, right? So if it coexists, for example, with co-dark matter, then this should contain the fluctuation sourced by other things. Does that help? Okay.
Yeah, so you mean everything added together?
Yes.
Okay.
Yes, but later I'm going to show you that at the very center of the galaxy is the self-gravitating thing. This thing itself is source of gravity. But that's on the next slide. Okay, so. Right, so for this, that comes from the structural formation is, let's say, is quasi-nonlinear because for lambda alpha, the observable is at the redshift around 5, so it's not that nonlinear yet. At the same time, an interesting question is that do we have totally independent observables that can constrain, that can just look for the effect of the quantum pressure so that we can probe or constrain ultralight dark matter? And then that brings us to the right side, which is the nonlinear regime. So if you look at the self-gravitating structures, or so-called solitons, if they form, they will have a characteristic size, and they form at the very center of the galaxies. That comes from the simulation. That's verified by simulation. So what is a soliton? Soliton is a self-gravitating structure where the soliton, the scalar itself sources the gravitational potential, and then this gravitational potential goes into the equation of motion, and these two terms sort of balance each other. So this is like the analogy of hydrogen atom, except that it's not a very central Coulomb potential, but is sourced by the whole distribution of the soliton itself. And if we solve this equation can be easily solved numerically. So one of the solutions can be given by this. You can see that also the shape roughly resembles the wave function of hydrogen atom, except that it's less peaked. And the two axes are just rescaled to demonstrate the shape. And in the simulation, people use this ansatz. It's a high power law to mimic the profile. And the price of this doesn't change much of the discussion. You can also use the exponential ansatz or other things. But the point is that this set of equations has a very distinguished scaling feature. That means if you tell me the area below it, then the shape is completely fixed. If you want to change the shape, the only way to do it is to increase the total mass, meaning that 30 more axions, or take out some axions. And these different solutions, they are just related to each other through this scaling factor. So in other words, this is a one parameter family of solutions that are connected by the rescaling. And the total mass fixes the shape. So there's no extra degree of freedom, at least for this vanilla type of image. Okay. And that gives us this interesting pipeline. That is to say, for any given soliton, if we are given a soliton mass, then the shape is fixed. And from the shape, we know the mass distribution. And from the mass distribution, we can derive the contribution to the rotation curve. Because if we put something localized in space, other test mass will rotate around it. So that means with any given soliton mass, we have a clear prediction of the contribution to the galactic kinematics. Okay, and then let's look more down in the data. So that brings us to the observables. And I only mentioned the soliton component, but inside galaxies, we have other components, the baryonic components, the gas, and some of the galaxies have a large-ish bulge at the center. So how do we do that? So in order to model this rotation velocity, we can either model each component and add them together. So luckily, for gravity, there's only one charge, so everything is additive. It only increases the velocity square. So that's one choice, to model everything and do that and marginalize over the irrelevant component. That's one exercise we did, but there's an easier way to estimate the effect. So another choice is to look at the soliton component. It has a clear prediction of V square. If this V square is already overshooting the observed rotation velocity, then adding other things won't help. It can only make the fit worse. So that's an alternative estimator. So let me use this cartoon to illustrate that. So x-axis, that's the distance from the galaxy center. Y-axis, that's the rotation velocity at the location. And suppose we have a bunch of data that's from the SPARC dataset. Now let's take one soliton mass. So the mass of the soliton is a free parameter, we vary that. And as I said, once we fix the mass, the shape is fixed. So we have a clear prediction of the rotation velocity. You can see that in some database, it overshoots the rotation velocity. In some database, it underfits it. And now the strategy is the following. We assume that for any bins that it underfits the data, it could in principle be fixed by an extra component. The stellar or the gas, maybe it's not completely fixed, but we don't know. So the strategy is that we mask out those bins that underfits the data and only look at this because, as I said, adding an extra component will only make these bins worse. So we count the chi-square of the overshooting bins by masking out the undershooting bins. And this way to be conservative, we only count those bins that's already masked up by the existence of soliton. Okay, and in the end, we compare this with the other method. It shows that indeed this is a conservative way to treat it. And from this, we can build the estimator. It's not really chi-square, but it's an estimator of the real chi-square. If we use that, we get this plot. Okay, so the x-axis is the scalar mass, and the y-axis is the allowed soliton mass inside each galaxy. Each curve corresponds to one galaxy. There are 170-ish galaxies from SPARC dataset. And what this curve tells us is that anything below this curve is allowed. You allow that much soliton to exist inside the galaxy, but above it, this region, that just means that you don't have enough room to pack that much soliton mass inside the galaxy. The kinematic data doesn't allow it. Okay, and I should stress that this is purely from observation. So I haven't told you, if you stare at this plot, it tells you how much soliton is allowed, but I haven't told you how much is expected from the theoretical point of view yet. Okay, so that's what I'm going to do next, to compare with theoretical expectation. Okay, so right now this is some observational found.
So the soliton is expressed in solar masses and the magnitude is 10 to the several, yeah?
Yes, right. I mean, it depends on the mass, right? But
Right.
sure.
I'm a little bit confused about how to interpret this plot.
Yes.
Because, I mean, if I have a galaxy that is 10 to the 10 solar masses, then certainly I can't have more soliton than that. I mean,
Very,
right?
very good.
This doesn't seem like a variable that you can,
So
maybe I'm not,
I
yeah.
guess you're worried about this region, like it allows that much soliton.
Right.
right?
Yeah, right, you can't, should you be able to compare how much soliton is allowed for galaxy without looking at the mass of the
Very good.
galaxy?
So this region is just tells us that the soliton is so extended because this is at a very light mass range. So only a small fraction
I
is
see.
contained within the data points that have rotation curve observation.
I see,
Okay, so this is purely from the data, as I said,
okay,
and I agree that in this region, it extends so much that it doesn't. I mean, in reality, it's not the real thing that we expect. But I haven't told you anything about the expectation
okay,
yet.
okay.
Yeah,
I'll-
data
I'll-
set.
yes, yes.
Yeah, okay, so here comes. So let's see, theoretical expectation. So from the simulations, we see that roughly there is a relation between the soliton existing in the galaxy and the property of the halo. So here the energy, so this is from the original empirical formula that this, the energy actually later is modified to kinetic energy. So let's say this is the kinetic energy to per particle mass versus the soliton mass. Okay, so these are from the simulation, and this is an empirical fit that shows that alpha equal to 1 in this relation is a good fit. But what is this relation? This relation can be rephrased by the following. So before I go here, first of all, from the simulation, get the blue data points. That is the distribution of the density. So here this is the density plot, and the x-axis is the radius. You can clearly see that within a small radius, you get a the distribution that follows the soliton distribution quite well. So the solid curve here is just the solution of the Schrödinger-Poisson equation for a self-gravitating static solid Bose-Einstein condensate system. Okay, so that's the solid curve, and it is consistent with the simulation quite well. And outside the radius, there's some tail that follows either FW or Burkhardt, but at large radius doesn't really matter. The point of this is that the place it matches these two together is determined, or say the size, the mass contained within the soliton is determined by this relation. This relation is the same as the one I showed you before, right here. And it's just a rephrase of the previous relation. So what this means is that the kinetic energy per soliton mass, per unit mass inside the soliton is the same as the kinetic energy per unit mass inside the halo on average. So that is the relation from the simulation. Originally, this was derived, this was found just empirically, but later this is better understood through the stimulated scattering, the Bose enhancement. So very roughly, I won't go into too much details, but very roughly speaking, the moment you satisfy these two relations, the excitation of the soliton will counterbalance the dynamic cooling, the formation of the soliton. So they will be in a quasi-static situation. The growth will be suppressed. Anyways, this is the relation for the soliton and the hosting halo. Okay, so remember that I said for soliton, it only has one free parameter. That is the total mass, or you can also look at the average kinetic energy. Once you fix that, the shape is fixed, everything is fixed. So here's the pipeline we use. So from the rotation curve, we look at the rotation velocity that is related to the velocity dispersion within the halo. Okay, there is an order factor here. I'm not showing, but in the computation, the code, we do have the accurate factor here. So from the rotation velocity, we relate that to the average kinetic energy inside the halo. And from the halo average kinetic energy, we relate that to the solid. And once we fix this, the soliton doesn't have extra degree of freedom. The total mass is completely fixed. So in other words, if we look at the rotation curve for each galaxy, we can see how much soliton actually is expected simply from the rotation velocity readout. Okay, so from down to up, this is the pipeline. And in this pipeline, the weakest chain, or say the hypothesis that needs to be tested is mostly this, right? Because this one, although it's motivated by the Bose enhancement is found in the simulation, but this relation is really the thing that we should test. And because, I mean, for example, for FW, this relation from the rotation to the dispersion is well known. It's just classical mechanics. There's nothing to go wrong. And from here, this is just a numerical solution with a soliton profile. There's no extra degree freedom. So in other words, if we test this pipeline, essentially we're testing the soliton halo relation. Now let's compare the theoretically expected value and the observationally allowed value. So we already saw that there's that much soliton allowed in the rotation curve in the previous plot. Now I divide this by the soliton halo, by the soliton mass predicted by the soliton halo relation. So that means anything above 1, that just means that the data is not strong enough to constrain the soliton such that even if there's a soliton predicted as big as the prediction of the simulation, the data won't be able to see it. But anything below 1, that just means that inside the kinematic data, there isn't enough room to pack in that big soliton predicted by the simulation. Okay, so this is just from one curve, the UGC 128. And if I look at a different galaxy, I get a different curve. I mean, galaxies, they have different sizes, they have different qualities of the data. And another one that covers a different range. Now, if I combine all 170 galaxies, I get this constraint. You can see that in a large mass range, there isn't enough room for the soliton to exist if this soliton is as big as the simulation prediction. So that's the M soliton halo. Okay, so that's how we test the soliton halo relation in a way that to see whether there's enough room for the kinematic data to allow the soliton to exist in the galaxy center.
I'm not sure I'm understanding how to think about this soliton halo relation.
Okay.
Should I interpret that it's telling me the division between kinetic energy and rest mass has to be the same for the dark and the visible stuff? Is that?
It's mostly all dark, because here we are just comparing. Suppose here we assume that there are some ultralight dark matter that has already cooled down to the ground state. Some of them haven't yet. Now you can check the scattering cross-section to go from excited to the ground versus from ground to the excited state. Okay, now for both, there's this Bose enhancement, right? So the phase space enhancement. But when this condition is met, these two enhancements sort of just cancel each other. And the excitation from the ground state to excited state is roughly the same as the cooling rate. That's why the growth of the soliton will be bottlenecked after this condition is reached. I think in the simulations, they saw that first it grows very fast until this is reached. And then it'll be not completely static, it'll be still logarithmic, but it becomes much slower. So roughly this condition is kept for a long time.
Sorry, maybe I haven't understood what halo means in that.
So yeah, maybe, okay, I should say that here we assume that ultralight dark matter is the component of the halo, and only a small fraction that forms soliton at the very center. Okay, yeah, I should say.
Sorry, no, I haven't. I should have.
Yeah. So even if soliton
Okay.
forms, it's a tiny fraction of the total dark matter.
I see. This
And
is
we are using this core, this soliton core, to and its impact on the kinematic data to constrain the size of the soliton.
I see.
Okay, and compare it with the expectation.
I see. And so what fraction of the mass is in the soliton versus the halo?
I don't have a number immediately,
Sure.
but it's way smaller, like it's below %. I mean,
Okay, okay,
right, because your halo
Yeah.
expands a lot bigger range.
I see. Okay, so yeah, sorry, I should have, this makes sense then. Good, thank you.
Okay, sorry, question.
Yeah, two related questions.
Okay.
First, the soliton halo relation
Uh-huh.
is observed for in the pure dark matter halo simulation, I guess.
Right,
Once you add baryons or
okay,
other things,
very good.
is that still hold or no?
Right,
Yeah, and then let me first finish my second question.
sure.
So second, all your observation data have some component of baryons
Mhm.
besides dark matter. So how do you separate these two components and then apply your soliton halo relation to infer the soliton mass?
Sorry, for the second question, I didn't
Yeah.
quite get it.
So for your observation,
Uh-huh,
I guess you have some information about the halo mass,
right.
and that halo mass have two components. One is the baryon, one is
okay,
dark matter.
Very good.
How do you separate this?
Okay, let me start with the second one. So for the second one, later I'll show you the fraction of baryons at the radius that we read out the rotation velocity that's used to infer the average dispersion. So you can see that at the radius of the rotation velocity that we use to infer that, the baryon, most of the constraints that show, most of the galaxies that show strong constraints are not baryon dominated. Okay, I'll show you a color plot with that. And there are some baryon dominated galaxies, but for those galaxies, the observation quality is also bad. So it doesn't put very strong constraints anyway. That's a very good question, actually, to check the baryon component, the impact of baryon component.
So you select those galaxies which dominate by dark matter.
I mean, this includes everything. So the one of the thing I want to stress here is that I'm not handpicking any galaxies. So I'm showing everything, but your concern is that what if these galaxies we mistakenly read out the rotation velocity that's not due to dark matter, but it's due to the baryons. So actually that's not the case. That's all I'm saying. Okay. But if I forgot in the end, please remind me to show you that the baryon components, the fractional baryons. And then for the first question, for the simulations, indeed, yeah, I think I passed that slide. Anyways, the simulation I showed you from the 2014 Shiv and company, that I believe only has dark matter. But then, yeah, I can't say much about the feedback effect. But if you look at just the baryon distortion of the soliton, it's very small. So if you look at that part, that the baryonic effect is a lot. I mean, for a lot of galaxies, is at a percentage level. Okay.
But if that distorts halo mass amount, then your relation doesn't hold.
Right. Yeah, I think there are indeed studies about how this whole formation would be affected by the baryon component. And yeah, so for that, that's not what I based on. Okay. So indeed, the simulation is dark matter. Yes.
What is the kinetic energy of the soliton?
Kinetic energy is the thing, is roughly the gravitational potential, because you need these two to balance each other. Right. So there's a self-gravity if you put a chunk of mass,
Yeah.
and it doesn't collapse. For fermions, if you squeeze it hard enough, that's the Fermi pressure. But here is the kinetic energy. Really, like if you want to call it uncertainty principle or something. Right, so it's the kinetic energy.
You get the kinetic energy from the gravitational potential. Is that how we calculate it?
Right, so if you look at the profile, there's a spatial derivative. And that derivative corresponds to the kinetic energy. You can think of it as a classical wave function, and then that gives you, the more squeezed, the more kinetic energy you expect, because they're the fast one. Okay. Good. So yeah, so the point is that even if I vary the soliton mass soliton halo relation by a factor of 2, actually this will be the bound we use, the lower part you can see that there's still a large mass range where the simulation predicted soliton halo mass, the simulation predicted soliton mass is in strong tension with the observed soliton mass, or say allowed soliton mass in the observation data. So even if we vary this relation by a factor 2, but that's also sort of to address potentially the uncertainty due to other sources in the simulation. And so later I'm going to only use this line to determine the range of the mass where it's in tension. Okay, so we theorists want to interpret things, right? So here we see there's a trouble. There's trouble between the simulation or simulation predicted value for the soliton and the actually observed kinematic data. So what are the interpretations? We could say that, oh, maybe the simulation people have something wrong in the simulation that's unidentified, or there could be some large systematics, maybe in the observation data of the rotation curve in SPARC dataset. But there's also another possibility that I'm going to take if I assume the simulation, if I assume the observation is right, then that simply says this scenario, ultralight dark matter is 100% dark matter. This scenario is not right. That's the source that causes this tension. Okay, so instead of just doing yes, no, fuzzy dark matter dead, then let's quantify this statement and say what is the cosmological constraint we can put on in order to get rid of that tension. So that brings us to the third part, and how do we suppress the formation of the soliton? So if ultralight dark matter is still there, and how do we not to form a soliton such that it's not constrained by the kinematic data? Okay, simply because the kinematic data only constrains the soliton part for now if we use SPARC. Now, in order to look at how to suppress the soliton, let's first look at how to build the soliton. How does the soliton form? We start with a chaotic initial condition, some random fields, and it starts to fragment. So that's the linear perturbation. And after a while, the halo forms, and inside the halo, it starts to cool down to the ground state, which is the Bose-Einstein condensate at the center. And during this process, this cooling can only happen in order for the scalars to shed off kinetic energy through scatterings. So that's the only source to cool it down. And one irreducible scattering source is the gravitational scattering with their own species, with the same particles. So suppose we look at a particle mass m tilde. I'll tell you why I'm using tilde here. So for each gravitational scattering, it changes the velocity by this amount. And now let's throw this particle into the galaxy, let it traverse the whole galaxy. The amount of velocity change will be given by this. So G is G Newton, and is the number of particles contained within the galaxy. R is the size of the galaxy with the velocity of particle. That's the mass. The log is just a Coulomb log due to long range force. So after one traverse of the galaxy, this is that much of velocity change. And what is the typical velocity to start with? Let's assume just a circular orbit in the beginning. The typical velocity is given just by this formula. And after many traverses, every time it changes delta V squared, and after this many traverses, the V will change so much that the amount of change will be comparable to the initial velocity. So that is the condition for it to get cooled down to the ground state. Or in other words, that's how many times the traversing it needs to forget its initial conditions in order to form the Bose-Einstein condensate. Okay, so this time scale is referred to as the dynamical relaxation time scale due to the gravitational encounterings. And every time you traverse the galaxy, it takes arguably this much time. So inverse of this, roughly 0.1 times n times each traverse that causes this much time, that's the time scale for it to cool down to the ground state. And that is the time for the soliton to form, roughly speaking, the dynamical relaxation time scale. And this is verified. Okay, I'll go back to just the one that I skipped. It's verified by the numerical simulation using the n-body simulation. And this factor is 1, very close to 1. That's a flux factor calibrated by the n-body. And you can write everything in terms of the local quantity. So what is the local quantity? As I said, at this mass range, 10 to the negative 20 around that, it's really just wave. It behaves like wave. If we want to look at the scattering of particles, we have to take into account the Bose enhancement, the phase space number density, meaning that the number of particles contained within each de Broglie wavelength blocks. And that is given by the number of particles times de Broglie wavelength cubic. So that is after, so another equivalent way to look at that is instead of looking at the ultralight scalar dark matter as the unit to do the scattering, we look at the so-called quasi-particles. That is the number of particles within one de Broglie wavelength block, and they scatter together because you cannot distinguish them due to the fact that they are identical particles. So that's why I'm using the M tilde. So these are the quasi-particles. That is the amount of mass contained within each de Broglie wavelength cube. And the mass of the galaxy can be written as the density of the galaxy, so on and so forth. So this is how I trade the previous formula here to the local quantities. So here you can see that rho is the density of the galaxy. It's a function of the radius for sure. And this is the dispersion velocity of the galaxy. R is the size of the galaxy, etc. So just to give you an idea, this is one benchmark that I wrote in a suggestive way. So you can see that the relaxation time scale will become longer for heavier particles. So if you go to heavy particles, your quasi-particle becomes less massive because the Broglie wavelength shrinks. And it takes longer time for it to form. It also depends on the density, because you have a lower density, then you expect less quasi-particles, lighter quasi-particles. And if this relaxation timescale is below the galaxy's age, there will not be enough time for it to form. That's one way to suppress the formation of the soliton. And how do we suppress it? The way we suppress it is that, so if you look at the relaxation timescale inside the galaxy, at different radius, the scale is different. We can always find a certain radius where beyond the galaxy, beyond that radius, it doesn't have enough time to relax yet. Within that radius, the relaxation time scale is shorter than the galaxy age, which is about 10 gigayear. Okay, and now let's see if ultralight dark matter is only one fraction, a small fraction of the total dark matter, rho will be smaller than this. Once you lower rho, the relaxation timescale increases. So that's how the fact that ultralight dark matter is a fraction of the total dark matter changes the relaxation timescale. And now if we plot out the relaxation time, the critical radius within which there's enough time to relax, but outside that, there isn't enough time to relax. The critical radius is a function of the fraction of ultralight dark matter. This fraction is a cosmological fraction. Okay, and it increases, the critical radius increases as the fraction increases. That simply means that the more ultralight dark matter is, the larger range you expect them to relax. And there's another quantity that is the supply radius. That's easier to understand. That simply means that within a certain radius, there's enough material for you to build one soliton. Okay, so that is the supply radius I call. And that just means that you need to go to that radius in order to collect enough ultralight dark matter to form one soliton. Now you put them together, we say that the soliton can only form if the relaxation radius is beyond the supply radius. That means for those solitons that you collect, they get enough time to relax during the age of the universe. Okay. But if you lower the fraction of ultralight dark matter to a point where they cross and below, then you don't have enough time, or say you don't have enough, either you don't have enough time or you don't have enough material for them to cool down to form the soliton you expect. Okay. And now let's look at the constraints we saw earlier. In this range, we see that the data is in tension with the observation. Now we need to suppress the soliton to form within this mass range. How do we suppress it? We take a mass here and plot out these two curves. We check what is the fraction we need in order to suppress the formation due to the relaxation constant. And we take another mass, we get a different two curves, we read out the fraction. So that is what the SPARC data is telling us. So SPARC data tells us if we form a soliton, it's in trouble with it. Observation. Now we should not allow the soliton to form for those mass range where there's a tension, and we can read out the required fraction in order to suppress it. So for a given galaxy, we can look at the fraction of ultraviolet dark matter as the total dark matter for a given scalar mass, and we get it covers a certain range. And for different galaxy, because the tension is at a different place, it covers a different mass range. And if we combine all of them, we see that in order to accommodate all the observations that are in tension with the simulation, the ultralight dark matter fraction needs to be below at the strongest place around maybe 20%. Although that this is from a very different system that has very different systematics, the bound is comparable to lambda alpha, and also it extends slightly to the heavier end of the mass range. Okay, so from this, we saw that the SPARC data constrains the soliton structure, but ultimately it can say something about the axion dark matter at the cosmological context in order to suppress the soliton to form. And then let me say a few words about the non-standard scenarios that might be fun to some of you. So for the non-standard scenarios, so now let me skip this. Suppose there's another axion species. Suppose there are two axion species and they have different mass. Then the relaxation timescale has 4 different scales, right? So we call it axion 1, axion 2. Then the axion 1 can gravitationally scatter with the same species, or it could dynamically relapse due to scattering between 1 and 2, or 2 and 1, or 2 and 2. So let's take species 1 for an example. The relaxation timescale should have the contribution from scattering with both species. So that is the timescale from one scatter with 1 or one scatter with 2. And now if I write it again in terms of the local quantities, you can see that this can be much above 1. So the inverse is much smaller than 1. If the second species, the spectator species, is lighter than the first species. Okay, simply because you expect a chunk of mass and the smaller guy just scatter with it, it quickly forgets its initial conditions. And as a benchmark, now if I put in a 10 to the negative 23 EV ultralight dark matter, that's only 10% fully allowed by lambda alpha bound. And I just put in the species like this and let it be there. And then you can see that for the range roughly above a few times 10 to the negative 23. So for the heavier guys, the relaxation is greatly enhanced by the existence of a lighter species. So that you need to lower the fraction much lower in order to suppress the formation of the first species to get a solid. Okay, so that's the coexisting case. And what about there's a self-interaction? So because we care about how these models are realized and how they are produced, so the Peccei scale is relevant here. And so for the previous discussion, I didn't include the self-interaction, but now let's see what it does. If we put in the self-interaction, it will have two effects. One is that it will also contribute to the dynamic relaxation. But at the same time, for this attractive type of particle interaction, it can potentially destabilize the soliton. Let me say a few words about each point. First of all, the previous estimate can be roughly done in a different way. Just use this Venn diagram. The cross section is just for the order of magnitude is given by 1 over m Planck to the 4th, velocity to the 4th because of massless, and m squared, m being part of here. And the relaxation time scale is given by 1 over m sigma v, but there's a phase-based enhancement that is the f here. This f is not a fraction, but phase-based enhancement. And put them together, we get this expression. So the phase-based gives us another copy of number density. So it's n squared here. And we can do the same thing for the 5-4 interaction. And now the relevant scale here is the Peccei-Quinn breaking scale. We can see that this one is quite similar to this one, except that the power of velocity is different simply because this is enhanced at low velocity. So there's a massless enhancement. That means if my Peccei-Quinn scale is a few orders of magnitude below the Planck scale, in principle, the relaxation can be enhanced due to this process. So that's the accelerated relaxation. But at the same time, it can also destabilize the soliton, meaning that if you look at the soliton profile, take some ansatz, say power law or exponential ansatz, we can derive the Hamiltonian or the total potential of the soliton. And what this, it all contains three terms: the contribution from the kinetic energy, contribution from the gravity, and contribution from the 5-4 self-interaction. Suppose I lower FPQ so that the self-interaction becomes stronger, eventually you will lose this local minimum. So this local minimum is the requirement for the soliton to exist as a self-gravitating structure. Ultimately, you will go to this curve, and the soliton will not cease to exist. Okay, so that's another effect. It's also cited a lot of times, for example, in the studies of boson stars. So this is all related. So now this is a very preliminary result from the work in progress. So we can check what the self-interaction does and how much it changes the band. So in the y-axis, I'm writing it as this alpha over 2 pi 1 over FPQ in a suggestive way so that it might be related to the axion photon coupling. But you can just think of it as a rescale of 1 over f. Ma is the axion mass, and the gray band is the misalignment, the usual misalignment band that requires in order to produce 100% dark matter. So in the gray region here, that's close to 100%. That means that the SPARC dataset can only constrain it up to this much FPQ, and it's allowed above and around. That's simply because above it, although the relaxation timescale is short, the axion is destroyed by the self-interaction. But of course, this is above the misalignment bound, so it might require some non-standard scenario that some of our audience is very familiar with. And the last one, let me use the last minute to say a few words about a different scenario. So their work down to construct even more exotic, non-standard axion-like particles with repulsive self-interaction. Now let's say, suppose we have a repulsive particle, and what it does. What does it do? And first of all, the accelerated relaxation will be the same because it doesn't care about the sign. So the interaction will happen similarly to the attractive particle. And furthermore, this interaction, not only it doesn't destabilize it, it stabilizes the whole soliton system. So you can see there's a flicker sign here. So there is always a local minimum, even if you crank up the soliton mass.
I have office hours.
Yeah, sure. And after this, if we put in everything, you can see that SPARC is a lot more sensitive to such type of solitons because it has enhanced the relaxation. At the same time, in this region, the soliton is not destroyed by the self-interaction. Okay, and of course, I didn't include this part, which is the distortion of the soliton profile because of the self-interaction. And after you include this, the final plot should be further modified, which I don't think I have included. Right. So, anyways, let me conclude. So hopefully, I entertained you a little bit about the interplay between the SPARC, the rotation data set, and axion dark matter. So in the first half, I showed you that if axion dark matter leads to the self-gravitating structures, they will form solitons, and these solitons is in strong tension with the SPARC data set. If we believe the simulations, then in a large mass range, the simulation predicted soliton that size is not allowed by the kinematic data. Then I showed you a few ways in order to suppress a soliton to form. And one natural way is to have ultralight dark matter not to be 100%. So that means this tension between the observation and simulation tells us there's a bound on the fraction of ultralight dark matter. And then I showed you a few variations with different axion potentials or multi-species where the bound can be either stronger or weaker due to the existence of this other interaction species. And thank you very much for your attention.
Great, thanks, Chen. We had a lot of questions during the talk, but yes.
Yeah, it's very interesting since that like yesterday at the World Journal Club, we also discussed something similar.
Okay.
If you notice, there's a paper recently archive, which claims if you have a repulsive self-interaction with lambda equal to like an order of 10 to negative 90.
Yeah. If your lambda is my f square over f square.
Yeah, exactly.
Okay.
Yeah, it's that thing, I think. Then it can fit all the rotation curve perfectly.
Okay.
But that seems not the same as what you conclude.
Okay.
In a preliminary results.
I'm not aware of that, but it's possible that this is due to the third effect, because as I said, this is very preliminary, and the third effect is that if you have the repulsive particle, and it can support the soliton to grow to a largish mass. But at the same time, it's no longer a one parameter family of solutions. So the shape will be further distorted a little bit. So I need to read that paper, but I assume it's possible that due to this, it's possible that because of this, the tension that I showed in the first part of the talk is modified. So it's no longer like this shape of the curves. Yeah, I'm sorry, I haven't read the paper, so I don't know much about it.
Curious if you
it's interesting. Yeah, sorry, one more comment is that regarding this distorting the soliton profile, the moment you have largish field value, this becomes important, it distorts it. But you also need to worry about other potential mode coupling and other things. I don't know if they looked at that. For example, you could induce particle number changing process because this nonlinear term is already large, right? So that means like 42 or 31 because this is a larger particles. So 31 is allowed, could be important. So you need to also check the lifetime of the soliton, whether it can be stable from that point of view, from the mode coupling point.
Any further questions? Let's thank Chen again. So, thank you. That's left.